During our earlier discussions, we have seen that the internal energy of an ideal gas is a function of the temperature alone. Now, using the kinetic theory of gases, we will justify our statement. And the topic that is discussed now is what is known as the kinetic interpretation of temperature, or how we are going to connect the temperature of a system using the kinetic theory of gases. So let's start from our idea of pressure exerted by ideal gas. So we have the pressure exerted by an ideal gas. P is equal to, hope you remember the equation, that is 1 by 3, we derived it finally, rho omega square, where omega square was the mean square speed. So this was the expression that we have used. Let me rewrite this equation in other form. 1 by 3, you know, rho was nothing but the mass per volume. I can start directly with this equation, but I'm just starting with this one, into omega square. Actually, we had gone in the reverse order in the previous derivation. So it's equal to, once again, 1 by 3. Capital M was the total mass of the sample, consisting of n number of atoms, each having atomic mass m. So I can write capital M as capital N into small m, where small m was the mass of a single atom, divided by V into omega square. Okay, so you can directly start from this equation. So this is the expression for the pressure exerted by an ideal gas. Now let me rearrange this equation. From this equation I can write therefore I'm cross multiplying V from the right side onto the left side. So PV, what would be PV equal to for the ideal gas? That would be equal to simply 1 by 3 N M omega square. 1 by 3 N M omega square. Let me say this is my second equation, right? But we already have the equation of state for an ideal gas, which is what also okay, PV equal to, simply that is equal to small n RT for an ideal gas. So let me say that is my third equation, that is the equation of state, EOS, for ideal gas. Okay, now what we can do, we can just equate the RHS of 2 and 3. So 2 and 3 will give you, so 2 and 3 gives, what is the thing you are going to get? I'll be getting 1 by 3 N M omega square, mean square speed, is equal to simply nRT. Okay, so let me call that some equation number 4. Now see here, m is the mass of a single atom or molecule of the ideal gas, and omega square is the mean square speed. So from this expression I can get the average kinetic energy of a gas molecule. Therefore, rearranging equation number 4, average, because it is mean square speed, kinetic energy, average Ke of the gas molecule, of the ideal gas molecule. Okay, gas molecule means per molecule. Okay, average kinetic energy of the gas molecule. Okay, well, how do you get it? M is the mass of the atom or molecule, so it will be half m into average speed is not square, so that is half m omega square, half m omega square. Okay, what will be that equal to? So here I'm putting half on the left side of equation number 4 and taking all of the things to the other side. So it will be equal to simply 3. I have taken it from the LHS of equation number 4, 3, and there should be a 2 in the bottom. Okay, because I adjusted. So then small n is already on the right side, RT, small n RT, and that capital N from this particular N I have taken to the other side, so that will be capital N on the denominator on the side. Is it okay? So that is, let me call that one as some equation number 5. These are all intermediate equations. You can avoid putting numbers for this one, right? That is the equation. We modify this one further. So what is the relation of number of moles with Avogadro number? So if you remember, we have what is number of moles n related to Avogadro number? N is equal to total number of particles or atoms in the sample divided by Avogadro number. Is not, how many Avogadro numbers are there in the total given sample of atoms. So small n is the number of moles. Number of moles will be equal to total number of atoms in the sample divided by Avogadro number. Okay, that was a definition of Avogadro number as well. So that is equal to, I can just substitute this particular thing where if you want, you can just mention what is Na. Na is the Avogadro number. Avogadro number. Okay, whose value you know, right? So substituting this one for small n, what will happen? Automatically equation number 5 becomes, so equation number 5 will become 5. What is 5? So it is half average kinetic energy of a gas molecule of ideal gas, half m omega square average, that will be equal to 3 by 2, right? So on substituting small n equal to n by Na, that n and n will be getting cancelled. So what is remaining is 1 by Na, right? So I can write RT by Na, RT by Na. Okay, that's let me call equation number 6 for the time being. But we have one more thing. This R is a fundamental constant and Na is another fundamental constant, Avogadro's number. So this R by Na is a new constant, which is another fundamental constant, which is familiar to this only we called what is known as the Boltzmann constant. This is a famous Boltzmann constant. Okay, so that is known as Kb. Okay, and this value, it's quite simple, you can obtain it. What is the value of standard value of R? It is 8.314 divided by Avogadro number is 6.02 into 10 to the power 23. So 8.314 divided by 6.0 into 10 to the power 23. So the 10 to the power 23 will just of course come to the top. Okay, so it will become 10 to the power minus 23. And the value of this Kb, so on substituting you'll be getting it. It's a 1.38. That is enough. You can take it up to maybe 4 decimals, 1.3807. Roughly take it as 1.38. Okay, into the power, it is quite easy to remember. If you remember the value of Avogadro number, it will be minus 23. Because Na is in the denominator, that will come to the numerator. You can clearly understand that. So R by Na, and the unit you can get, that is Joule per Kelvin. Joule per Kelvin. Okay, remember it's a very important fundamental constant in thermodynamics as well as statistical mechanics, or in modern physics you can take. So it's well and good you remember this particular relationship. That will be handy for you in many other situations. Both the relation of Kb with the Avogadro number and its numerical value has to be memorized. It will be useful for you later also. So you need not memorize always as 1.38 times 10 raised to minus 23. I just tell you that just remember this one roughly, as that will be enough. Within errors 1.4 into, okay, 1.4 into the power. Power is easily memorized because it's Avogadro number. If you relate it, 10 to the power minus 23. Plus 23 becomes minus 23. So using this Boltzmann constant, now I can rewrite equation number 6. So what would be the equation number 6 becoming? So this is further equal to 3 by 2. 3 by 2. Hope you remember all these equations. Somewhere you have seen this equation. 3 by 2 kBt. 3 by 2 kBt. Okay. So that's our average kinetic energy per molecule of an ideal gas. So Ke average, if you want, you can just say that this is nothing but the average kinetic energy. I can call Ke average, which is equal to half m into mean square speed. So that is my final expression here. Okay, and this equation will help us to interpret the idea of temperature using kinetic theory. Let's go to the kinetic interpretation. Now you can just rearrange this expression. Actually, you can rearrange this expression. So I can rearrange this expression. What I get, I'm just using the space here. Okay, so let me use the space here. Yeah, right. So I'm writing question number 7. So what is the equation number 7 telling you? Ke average is equal to 3 by 2 kBT. Okay, so let me rearrange this one. That is T equal to, because we need to interpret temperature. T is equal to, what do we T equal to? 2 by, is not, I'm taking all other terms to the side, 2 by 3 kb, 2 by 3 kb into Ke average, is not, into average kinetic energy, Ke average. Okay, remember this is for per molecule actually, okay, of the ideal gas. So 2 is a constant, 3 is constant, Kb is another constant. So what is the conclusion? Therefore, the conclusion is straightforward. That is the temperature of the ideal gas sample that is directly proportional to the average kinetic energy, is not, average kinetic energy, Ke average of the molecules. It's understood, of the molecules of the ideal gas, of the molecules. And hope you remember this particular result provides an interpretation of temperature based on the kinetic theory of gases. We had already established this fact already, okay, earlier. That is, the temperature of an ideal gas is not, the temperature of an ideal gas is directly proportional to the average kinetic energy of its atoms, and that is why you wrote, hope you remember, that in the case of ideal gas we have written U is a function of temperature alone. Okay, because the potential energy contribution for ideal gas is 0 as per kinetic theory. There is no intermolecular interaction, so the internal energy is purely kinetic in the case of ideal gas. So this is the interpretation, kinetic interpretation of temperature in the case of an ideal gas. Okay, that's about it.